Alrighty then. It says we're live. Oh no, I'm not wearing sunglasses. That's okay. There's some reading to do. Hey guys, what's going on? Memes here. And today, I will not belay the point. We're not going to be talking about spherical cows or the Einstein kappa constant. No, we're going to be talking about the Higgs boson self-coupling constant. I'm not gonna pretend like I know what that was like years ago or anything. It's like you come across these things. Apparently, the Higgs likes to interact with itself according to our standard model formulation. Again, I'm not gonna pretend like I'm a mathematician. I do not have a PhD in physics nor mathematics. I'm a dude on the internet that's interested in this stuff that happens to have access to a lot of the modern computational techniques and, I don't know, hundreds of years of humanity's hard fought experiments to gain data and numbers and everything. Um, yeah, so that's what we're doing. Oh, hey Rick, I may or may not actually feel worthy now. We can talk later. Let's just say I may or may not see the power of radicals now. That's a story for a different day. Um, but so while looking at different stuff, it's like, all right, you come across things. You go to Wikipedia. You use it as a platform. You go to different articles. You go to Physics Stack Exchange. You go to all these different things. It's like, all right, well, these are what very smart people have worked years on to develop our modern standard model formulation. U1 cross SU2 cross SU3, whatever that is. I have all their Lie groups and stuff like that. Some mathematical representations that seem to be able to model our reality. I'm just a monkey with a magic typewriter and I just pattern match and stuff like that. I'm literally just a lame language model, I claim. Okay, so let's actually get into this whole thing. I put literally the links to all this stuff down below. Oh yes, it's a new shirt. I bought 7 of them, one for each day of the week. Thank you. Um, all right, so let's just jump into this. Let's go over here. Blah blah blah. Show class. All right, where are we? This guy here. All right. Full disclosure, there are a bunch of assumptions and stuff like this baked in. This is probably just a coincidence. It happened to be a coincidence that seemed to match the data very well in one instance. It actually literally was the best answer. So that's why I entertained it. I made and again, I've put out different values and different formulations for this, and I've gone back and forth a couple of times. I'm just I'm looking for simplicity. And I kind of showed some of this stuff to Casey the other day, and hopefully I'll see him in another couple of weeks. Um, He basically pointed out, it's like, well, one of the things I'm showing, it's like, well, these are just basic building blocks. It's like, well, duh, you're always going to see these things. Now, again, we need to follow experimentation and everything, and as we get more significant digits, we can see. Because if you see a pattern, it's like, oh, look, Planck momentum. It's 6.2. It's obviously 2 pi at magnitude 1. We could only be so lucky. No, it's 6.25, or probably more likely 6.249, blah, blah, blah. Yeah. When you only have so much data, especially if there's rounding, and yeah, be wary. So let's get right into this. Okay, so this is my conjecture. Maybe this is true, maybe this isn't. If not, it does seem to match current data pretty well. So the claim is you take h bar, the unit of action, you divide it by the reference of action, the joule second. You take that square root ratio, you multiply it by the Planck mass. You basically get the modern value for the Higgs mass, or at least this is actually terrifyingly exactly what C. There's some rounding in here. There's actually like 3.76 or so, and that's the number we're going to use. But if we look up, we can do this right now. What's it? CMS Higgs mass, something like this. Okay, that was the one from a couple of years ago. So they've... Okay, oh, that was before. That was Atlas from earlier. I don't know the video. All I know is they returned that, and I'm just like, well, that's weird, because they're like... Irregardless, I can say that because I'm still in Boston. So, who knows? And again, it's speculation. It's speculation. Could we only be so lucky that it happens to be the root of magnitude of h bar? We'll see. Okay, so that's a claim. That's a claim. We want to be more specific here because Wolfram Alpha only has so many significant digits. All right. So we go to CODATA. You get the Planck mass here. All right, so you can see I literally just copied and pasted the extra digits in. Okay, that gives us this. And again, there's... So the digits within the one standard deviation of error. There's gonna be some... This is gonna be a math-heavy video. Now, most of these things, there's links there. Again, don't trust me. Feel free to verify. So this could go down by 0.24 or up by 0.24. And I may or may not have checked before we did this just to make sure that it at least falls within the error values of the crazy things I'm going to claim. So, or at least have an explanation. All right. So we get this over here. Yeah, so it's a little bit more precise. So now we at least have more significant digits to play with. Again, could be totally wrong. And then we multiply by c squared to get our energy here. 3.6. It has the 1. I can show you the stuff with the 1 again. It doesn't match quite as nice, but then again, I'm looking for something to latch onto. Something very simple that we could say, okay, we have a high confidence that something so simple might hold. Maybe we can look and, I don't know, maybe the thing's tuned a particular way, so to speak. Maybe there's going to be some wonderful music that will be played. I claim. Okay. So, yep. Oh, I'm gonna go with it was okay. So I'm not gonna do that right now, Rick. All I know is I was looking at the mathematical formulation of the standard model. They give the example of let's skip ahead very slightly. Where are we? Okay. So I was looking at stuff like this. It's like, okay, so the fine structure constant for quantum electrodynamics, QED. Basically, they started formulating this, and I always got confused about like the G's and stuff. It's like, wait a second. That's just a gauge coupling. Because when I look at these things, I'm like, well, that's this and that. I'm like, well, the fine structure constant is elementary charge squared. So I'm like, well, that's going to be elementary charge 1, elementary charge 2. Oh, wait, no, that is squared, though. Okay, never mind. Long story short, I was playing off with the general structure of the alpha thing, and may or may not have been plugging some of these values in, and I got into a little bit of a loop. Or some may say something harmonious came out, but we can get to that later. I don't want to discuss things that I'm not supposed to publicly. I digress. Okay. So, we've got some extra significant digits. All right. Where are we going with this? We're going to Fermi. Why? The Fermi interaction. And again, links to all this stuff. So is in the links below and everything. And again, a lot of stuff is Wikipedia. But then again, this also... I'm familiar with the format. It seems to have pretty up-to-date information. And it also seems to appear in some papers and stuff, too. And occasionally some papers and other things get it wrong. So does Wikipedia and even Math World, but I digress. Okay. why am I showing you this crazy thing? Well, aside from just an exercise of just playing around and seeing what's going on, um, what we're looking for is what's called the Higgs boson vacuum expectation value. The keywords that you'll hear often are VEV. You're like, what is that? VEV, vacuum expectation value. And it often will redirect you to the Higgs vacuum expectation value. So that's defined as the square root of 2 times, this is the reduced Fermi coupling constant. If you just type in Fermi constant, it's kind of like h bar. People will say Planck's constant, even though that's not what it is. It's the reduced Fermi constant, often referred to as just the Fermi constant. That times root 2, square root that whole thing and put 1 over it. So it's the negative square root. So it's basically 1 over the square root of that whole dang thing. It's approximately 246.22 giga-electron volts. So it's a wee bit under the mass energy of 2 Higgs bosons. Okay. And then you go through this, and you can do these calculations for the W and the Z boson, and then you'll get the Weinberg angle and everything. All this different stuff that we seem to be able to use to calculate and formulate the standard model. Fantastic. Okay. Why am I showing you this? Because, well, let's go over to CODATA. Let's get the Fermi coupling constant. All right, so it's got the full Fermi divided by h bar c, which, at least according to Wolfram Alpha, is the bending stiffness, aka the Newtonian gravitational constant, with a Planck mass in the numerator. It's an interesting thing. And that's cubed. Why? I don't know. We're talking about some volume or something? Maybe. All right. But we're really only just coming over here to snag this number. All right, we're snagging this number. It's got like an error of 6 in the last digit, so that could go up to 9.3 or 8.1 within 1 standard deviation. All right. So let's plug that all in. So we've got our root. Where did I put that? Over here. All right. Root 2, reduced Fermi constant, raised to the negative 1/2. All right. Square root 2 times the reduced Fermi constant that we just copied and pasted from CODATA, raised to the negative square root, gives us, okay, yeah, it is really close to 246.22 giga-electron volts. We're trying to eke out a little bit more, see if we can't see what might be going on. Okay. We got that. The erg is a very underappreciated, depreciated unit, I claim. Okay. So I got this number here. Where are we going from here? Well, let us continue. Again, we're back at Wikipedia. What the heck is this? This is the long page. The mathematical formulation of the standard model. All right. For a less mathematical description of you see standard model. Oh, no. I want to see all the things I don't understand. All right, so we got our SU3 cross SU2 cross U1. All right. So it seems to be able to describe most of the stuff and things that are going on as far as we understand. All right, we got all that stuff there. Going down, 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 down. All right. So basically they have your free parameters here. Technically you would need 7 more to include the neutrinos, but for the 19 that they have, this is what we got. Okay. So as we can see there, it has a 6 with a slightly closed one, but I'm just going to go with CODATA. It's at a 7 there. This was the Higgs mass from, I think, a few years ago. I'm going to go with my baked-in assumptions. Why? Because, 1, I'm narcissistic. 2, it's a very beautiful thing, I claim. I just need to get over the hump of, if there was something to that, that would mean the joule second would have some significance. Yes. Maybe. I don't know. I mean, what is the chance of us doing something so spectacularly awesome, and we managed to get extraordinarily useful units that we could actually coherently think of. I mean, what are the chances of that? That would be, I think, by definition, a miracle. Okay, the real reason we're going here is, and we were looking at this a little bit before. So we go over this, we got our different couplings and everything like this. Okay. So, so the Higgs mass you could use because, well, one's there as one of the free parameters. However, we apparently could use the Higgs self-coupling strength. So it's this lambda here. Okay. So, and that is equal to the mass of the Higgs squared divided by 2 of that vacuum expectation value squared. You kind of look at this, you're like, oh, why is there a 2 there? We like to put 2's in places because apparently it seems to make sense. Very often you'll see something like, I think usually was the Schrodinger equation very often will start off as something like, I don't know, like h bar, like negative h bar squared divided by 2m or something like that. So it seems to be very often we're doing some 1/2. It was that kinetic energy or something. I think Rick would know. But yes, a noob. But we got this coupling strength. All right. So I take the mass of the legs, we square it. And then we divide by 2 of those vacuum expectation value thingies that we calculated over here. All right. So what we need to do is we're going to square this thing. Excuse me. We're going to square it, multiply it by 2, and we're going to divide this whole dang thing into our earlier calculation for the Higgs mass squared. Okay. Because that's what it says. And it even tells us it comes out to be approximately 0.129. About 0.13. All right, so it's got that. So let's do that. So again, I dropped the 1 because again, there's some error there, and it makes my argument cleaner. So I'm just full disclosure. If I put this at the upper limit, I think I go through a couple of calculations there. So it does have a wee bit of deviation, and occasionally there might be some agreement there at a particular configuration, because as you can see, I'm literally just changing the numbers here. And it's easy to see that way. So okay. All right. I realize it's changing depending on how I had it set in. I apologize for that. Okay. So let's just go back to our earlier. All right. We have this number here, and again, this is my conjectured value of the Higgs. This is the vacuum expectation value, literally calculated from information from CODATA and based upon the VEV, or vacuum expectation calculation. Okay. So this is the Higgs boson, mass energy squared, just like we have over here. Okay. And then we're dividing it by 2 of those VEVs squared. We got 2 VEVs squared. Make sure I have okay. Sometimes the parentheses and stuff matter. It's commutativity is an important, often underappreciated thing, I claim. All right. So long story short is we get this value right here, 0.12964. I have no idea what the heck that means. So, let's look. Might this have any meaning? Is there something simple that we could find that also seems to match the data well? Take a look. All right, it's going to go to some possible closed forms. 7/54, 4 pi. All right, so like a sphere divided by 97, 33 over 800. Some logs there, Oh, as you can see, it's still loading. Yes, I may or may not have given away what might be going on. Okay. You see all these things here. What looks most simple? That's kind of good. Okay. Long story short is the one thing that seemed the simplest, that also happened to get all the significant digits, was 3 over G sub GE. What the heck is that thing? Well, got our little table of contents here. It's like G sub GE is Gelfond's constant. What the heck is a Gelfond's constant? Well, let's take a look. Gelfond's constant. In mathematics, the exponential of pi, aka e to the pi. E to the pi. The base of natural logarithms raised to the constant of circular curvature. That's interesting. Also called Gelfond's constant, is a real number e raised to the power of pi. All right. Well, there's decimal expansion, blah, blah, blah. All right, so like both e and pi, this is irrational and transcendental. Okay, it's all this stuff, blah, blah. Oh, look, it also happens to be, e to the I pi raised to the negative I, or negative 1 raised to the negative I. That's interesting. It's the e to the pi constant appears in the relation to volumes of hyperspheres. That's cool. So summing up all even-dimensional unit sphere volumes and utilizing the series expansion of the exponential function gives e to the pi. Oh, so it has to be the sum of all even-dimensional hyperspheres. That seems like a neat thing. Okay. All right, that's an interesting thing, but oh. Hey, K-Shell. Thank you, Rick. I'm gonna save that guy for later. Don't mind me. I'm totally just not screenshots. Okay, there we go. Thank you. All right. We got Bishop. Welcome, Bishop. Good to see you. Hey, welcome, Violence. We got some XYZ. Ah, yes. Uh-oh, did E ate the pie? E-A the pie. I was going to say E ate the pie. Did E ate the pie, or is that E ate with pie? I'm sorry. My mind just branched into a whole bunch of different areas. I apologize. Okay. So we've got Gelfond's constant here. All right. So why am I showing you this? Okay. Because number one, this happens to be the best fit for the Higgs vacuum expectation value that I found. So long story short, as we take this, it was 3 over Gelfond's constant, so it's literally 3 divided by e raised to the pi. Okay. And that gives us this number. So the next digit would be 1. At least within the error bars there and everything, this seems to be feasible. Now, it would still need to line up with all the other data and stuff we have. There's another reason why I'm showing you this, because this stream is titled The Higgs Self-Interaction and Weak Sector Masses. Now, I see this. I'm like, this is kind of cool. It seems to fit pretty well. We just happen to have, I don't know, Gelfond's constant, or the base of natural logarithms raised to the constant of curvature. Happens to be the sum of all even-dimensional hyperspheres. I don't know, do we live in an even-dimensional hypersphere? Who knows? And then, okay, we're dividing that into 3. Looks like we live in like 3 spatial dimensions. I don't know. Is it 3 generations of particles or something like that? Or is this might just be a clue? Might just be a common thing. Because it's e to the pi, that doesn't mean there's anything there. Now, In order to make an argument for this, I'm going to need to do better than memes. You only got like maybe like 4 or 5 significant gadgets, maybe 6 or something like that. You need to do better. You're going to need to see if maybe there's some more commonality. Can we bolster our argument? That doesn't mean it's right, but I'm at least looking for evidence that might make us go, maybe there is some there, and maybe it's worth probing a bit more. And if that's not where experiment and reality tells us it's there, then it's wrong. That's all. That's all. Most ideas are wrong. Okay. So the reason why I'm showing you this isn't just because of this, to be fair. I think maybe we mentioned a little bit of this before. But let's go ahead. Let's go to our weak sector. And this is the thing that always kind of boggled my mind. You hear about the quarks and everything, or whatever that may or may not be. And for some reason, the top quark, it's the beefiest of all the quarks, seems to live in the weak sector. I don't make the rules. Okay. Long story short is, we're just looking at the data. See where the data takes us. Okay. So this was from last year. Okay. Maybe this has been revised. Maybe it's changed. I don't think it's probably changed that much. Long story short is a result here. The top quark mass, and this is in giga electron volts. Okay. So 1 billion electron volts. Electron volt tends to, at least for observers like us, a very small thing. 2 GeV is about the magnitude of a lightning strike. So yeah, it's a lot of energy. Oh wait, no. Sorry, no, that was off. 10 to the 19 GeV is about the strike of a lightning bolt, because the Planck energy. I was only off by like 19 orders of magnitude, derp. Okay. Long story short, mass of the top quark. It's approximately 172.52 giga-electron volts. So it's got an error or an uncertainty of about 0.33. So, all right. So about 0.33 up, 0.33 down. That's what we believe it to be. All right. So let's ask some questions to Wolfram Alpha. Let's take the top quark mass, just straight from that paper, and let's divide it by our conjectured mass for the Higgs boson. Again, using the root of action as a scalar times the Planck mass. Okay. We do that out, we get this ratio here. Okay. Now again, 1.37. I mean, I like that anytime I see 137. It's not 0.35999. Yeah, it's not the Fine-Structure constant. But this seems to be the ratio between the mass of the top quark and the Higgs boson mass. Okay. Might there be a potential closed form for this? So I asked the question. And we see some good candidates here. It's like, all right, this is very pretty here. Wait a second. Why is E and pi here? Let's keep going. We can get back to that. We're going back to that. Okay. This is interesting. And again, it's not the best match, but occasionally if something fits very well, maybe you should question why. Either maybe it is something fundamental, or like Professor Sean Carroll said, sometimes it's just a coincidence. Well, this is interesting because this is not E raised to the pi. That's actually E raised to 1 over pi. Huh. I know Rick, Thad, and God rest his soul, John Williamson, have expressed to me how looking at things from perhaps an inverse perspective can yield interesting results. Okay. So, no, there's no way the Higgs coupling constant could be related to E raised to the pi, the sum of all even dimensional hypersphere is being divided into three. I mean, that would just be weird. And then being able to calculate the ratio between the top quark mass and the Higgs mass, and that would be e raised to 1 over pi. I mean, that would just be absurd. What would happen? So if we take our calculated mass of the Higgs boson, again, that's based upon this, we're taking the quantum of action, Planck's reduced constant, we're dividing the dimensions out. We're doing the naive thing of dividing it by its reference of action, the joule second, and we're taking the square root, multiplying it by the Planck mass, which is a natural unit. This is technically a natural unit too. It's a natural unit of action. We get this right here that matches quite well with the recent CMS measurement they had put out earlier in the year. It came out to be precisely that, but there is some rounding there. So we're using, basically we're using like this number here. And I dropped the last digit just to empower my argument. So I just want that to be clear so I'm not hiding something. Except that extra digit. All right. So we go back over here, and this is what we did. So we're taking this value we calculated for the Higgs boson mass. We're multiplying it by the pi root of e. Does that even make sense? Or e raised to 1 over pi. Gives us this, 172.37 giga-electron volts. 172.37. 172.53, that's an error of 0.33 GeV. Well, that's well within the lower bounds of the current best measurements, it seems, of the top quark. That's kind of cool. But again, you would need to see a consistent pattern for something like this to even remotely be able to say, well, maybe there's something there. All right, well, let's continue, shall we? Let's take a look at the Z boson mass. You guys might like this. But so this was so this was last revised 3 days ago. Cool. Submitted 21st of May of this year. All right. So the mass of the Z boson, as of this, it appears to have a mass of, and this is in mega electron volts, so you'd you move the decimal point over, so it would be over here. So it's 91 point, hold on, I have it over here. I just copied and pasted it right from there. Key thing to keep in mind, it's got an error of about 12 mega electron volts. Okay. So, 91, let me just make sure the math is right. 9118, and 57. All right, 57, we convert it into GeV, cool. Let's look at the ratio of the Z boson being divided into the Planck mass. 1.375. Oh, that's interesting. Wait, why does this number look familiar? This 1.376. What? 1.376, 1.375. Wait a second. This is the mass of the top quark being divided by the Higgs boson for 1.376. This is the mass of the Higgs being divided by the Z boson, 1.375. Well, that's a coinky-dink. What might that number be? We ask Wolfram Alpha. Wolfram Alpha, what might a potential possible closed form for something like this be? Let's take a look. Oh, the pi root of e, or e raised to the pi. This version has, the last one was 6. Okay, so if we extend it out and that went up, it's okay. That's interesting. That's also very interesting. Um, but for the sake of our current discussion, what would happen if we assume this would hold? That it would it would literally have the same form as something like this. We're multiplying the mass of the Higgs boson by e raised to 1 over pi? That seems to give us, at least on the within the 1 sigma current estimates of the top quark, it seems to be well within the 1 sigma range. And we just multiplied it by e to 1 over pi, or pi root of e. What happens if we were to do that and, let's say, I don't know, take the mass of the Higgs boson and divide it by e raised to 1 over pi, or the pi root of e? We get 91.196 GeV. Okay. We had 91.19, but oh, wait. The upper end of the error is 12, so that means we could add 12 to this. That's going to go to a 9. That's going to go to a 7. Okay, so that could be 91.197. 91.196. That seems to be within 1 error. It's close to the top edge of the 1 sigma, but that seems to be pretty darn close to the mass of the Z boson. Now, the interesting thing here is the proportionality, the distance from the Higgs boson to the top quark mass and the Z boson seems to be really damn close. Is it actually the pi root of e? I don't know. We're going to need to follow, again, our measurements, our data, and, if possible, try to simplify things as much as we can. Because if we can explain more with less, then we go from just simple numerology to, I don't know, the prevailing thought of the time. It's and again, you also don't want to break everything else, and that's why it's like, well, what are some factors I see all over the place? Pi, E, you see it in math all the time. You see it in physics all the time. Might these be good? And to be fair, as Casey pointed out, well, these are basic building blocks. I'm just leveraging the vast sum total knowledge of humanity in modern computational tools. Just asking some basic questions, seeing where it goes. Okay. Now, could we, I don't know, is this called running the table? I'm not going to say run the table, because I'm not going to, the entire weak sector or something like that. But let's take a look at the W boson mass. All right, this is from December of last year. All right. So right now we've got 80.360. So 80.360 GeV, and then about 10 over here. So that could go up to about 70 there. Seems to be in agreement with the standard model, and that's 1 standard deviation. So what do we get? So as Thad had done before, we're literally just taking what we did over here for the Z boson mass. So we are making an assumption that it would be this, and this number, we must remember, is towards the upper end of the 1 sigma relationship, or the 1 sigma value for the Z boson mass. Okay. Now, it might be within it, but it is towards the upper end. Okay. Now, that had basically found what seems to hold for the weak mixing angle. Should we go through that right here? I think we can go. Do I remember what it is? Hold on, let's actually do this. CODATA, not Fermi energy. I'll just click on it. So just go to the link. Weak mixing angle. The claim is it's okay. Basically, it gives you this. You have to have 1 over the W boson mass divided by the Z boson mass squared. But basically, yeah, you set up like this. So you got sine squared over that weak mixing angle. Long story short is that found the best, simplest fit was hyperbolic sine of -1 to the 1. All right. Let's see if I can actually do this without screwing it up. Okay. Let me just see which value this kicks out. Okay. So, how do we do this again? I'm going to embarrass myself, aren't I? Do I just do sine squared? Is that what it is? Sine squared. Bracket all that for protection. Nope. Okay, I'll just put in the values. It's the weak mixing angle. He found this ratio. Oh god, I should be able to do this because I had to do this before. Oh, it was 1 minus. So weak mixing angle is. Oh wait. So 1 minus. Nope. All right, let's just put in the values. So it's W divided by Z. Let's just go grab our W value here. So W value, put it over here. Our Z value, oh, no, let's top quark. Pop out our Z value. Steal that there. So it was W over Z. Bracket everything up. All right, and I think it was that whole thing squared, right? Let's see. W mass divided by Z mass squared, and then minus 1. All right, 1 minus. Okay. So that gives us a weak mixing angle of 0.2232. Weak mixing angle, best measurement is 0.22305 with an error of 23. Yeah. Okay. So 0.223, 0.2232, that's within the weak mixing angle ratio there. And again, does that mean it's right? No. We're just trying to find and match what might be actually going on as simple as we can. Now, again, I'm not going to say, oh, this is obviously how it is. I mean, that would be crazy. Like, oh, very simplistic thing matches a couple of significant digits. No. We follow measurement, but the whole concept is utilizing modern tools, modern measurements, and stuff like this. I mean, come on. It's like, oh, where was that? I ain't no Einstein. God, that looks terrible. I'm gonna do it on the internet. I'm just looking for ways to simplify things or take the vast amount of information that we have and maybe do some naive things, make a lot of mistakes. Because, I mean, if you don't make mistakes, how are you gonna learn? It's like, you can't really do something right until you've done it wrong. I mean, or maybe you're extremely blessed and gifted, by all means. I apologize. Let me take a sip of my slightly watered down coffee and get back to the chat. My apologies, everyone. That would be a very interesting interpretation. I didn't even think of that. Oh, cool. All right. So the long story short is let's go back to our back to our thingy here, just for sake of argument, and to not say, oh my god, we're all. Where is this? Okay. Long story short is, thank you, Thad. This is what Thad had come up with, and this is utilizing what he had calculated that maybe, just may. Oh, I'm looking at this. I wonder what would happen if we just did this. 1. Just don't mind me. I'm a curious soul. I just want to divide this into this now. I'm sorry. This is like literally what I do. It's just like I look at things and I'm like, oh, that's a shiny thing. Let me do this. Let me do this. And a lot of times it's like, oh, I'm just so naive. I don't even know what it is. 1 pi over 1 plus log plus root 2. Oh, because this is also, you can also write it as log of 1 plus root 2. That is also why. Okay, that's... Oh, is there any... Okay, it doesn't appear to be any easily derivable closed forms. Okay, cool. All right, but we need to point out this is outside the error bars. We need to be honest about these things, because when we do this calculation, it's 80.377 giga-electron volts. According to the paper that we were just looking at, sorry, skipped ahead. All right, this is 80.360, 0.2, but it can go up by about 10. All right, so the upper limit on the 1 sigma is 80.37 giga-electron volts. This is outside by 7 mega-electron volts, because this is hundreds of mega-electron volts. This is tens. This is single electron volts, because it's base 10 power. This is giga and then mega. I learned that stuff from Final Fantasy on the Bahamut summons. It's mega flare, giga flare, terror flare. Yes, I learned I learned my base exponential, not base, but the 1,000 plus exponential powers from a video game. All right, so basically it's within 2 sigma of the currently generally accepted measurements for the W boson. Okay. Why did I have this other thing here? Okay. So this is, again, when was this paper? This paper was, I think, December of last year. Okay. So I think it was submitted there, but they still have the same measurement in here. Because it's CERN, and of course they do. All right, so they're probing it. So, all right, in the standard model, the W mass is related closely to the strength interaction underlying the electromagnetic and weak forces to the masses of the Higgs boson and the top quark, okay? Which constrain its value to 80.353 million electron volts. All right, so that's lower. That is basically outside the standard model with an uncertainty of 6, so it could go up to about, that would become a 9, so that'd be about 3.60. So basically, around the measurement it is there. Measuring the boson, W boson mass with high precision, therefore makes it possible to test whether or not these properties all align in a way that's consistent with the standard model. If they don't, the cause would be could be new physics phenomena, such as new particles or interactions. Okay. So if we were to take this, and we were to do 6, bring that up there. All right, so this calculation is about, what, 3.5 sigma? 3.5 sigma from the standard model? I mean, that's not really new particle physics. You need at least 5 sigma, and you need to be verified by more than one experiment. So, just because sometimes we're wrong. Okay. Now, the interesting thing, and the part that I'm slightly bolstering my case for, is a slight anomaly. Because the W boson has measured ever more precisely by several collider experiments, including ATLAS, LHCb, the Large Hadron Collider, In 2022, there was a surprisingly high value of a smash measured by the CDF experiment. It plunged the particle into midlife crisis. So basically, it had a much larger. It was like I think like 20 sigma off, maybe 40 or 50. It was basically at one point they measured it at 80.433.5 giga electron volts. Yes. And they had a really small uncertainty. So about the same uncertainty as we just had, but it was, what is it? They had standard models like 353. Yeah, 353 for those the next three after the 80. So yeah, that was quite a large difference. Yeah. So of course it's gonna call for more studies because that's way out of the ballpark there. But okay, we have these other measurements. All right, that was within the prediction that we had. That was from an early run. This is the most recent thing that we had there from the paper there. Maybe they've had another one. At least I didn't see. Okay, this is the main thing. This is listed as the diagram of the measurements here. Okay, so, all right. The LEP combination, 80.376. But yeah, the last two digits are down by 33. That's pretty wide. It also falls precariously close to that prediction there. But just because we want it to be true doesn't mean it is. Okay. We got this, which was close, but then again, it's got a pretty big spread there. And as we can see, most of these are within the standard model, and that's at 80.353 there. Okay. And we had this outlier over here, this outlier over there. Okay, yeah, and it also had really small error bars. I mean, it had ginormous error bars, but are we really getting anything out of it at that point? It's like, okay, it's telling us maybe something. But it is interesting it had a blip up there, so maybe, again, this is an incredibly hard thing to detect. We had this one that basically came in right at the standard model, still had pretty large error bars. We had this other Atlas experiment. As we can see, that had fairly large error bars, and that was, oh, actually, no, much smaller error bars. Other than at least a lot of these other ones, except for the CDF, which it does seem to be an outlier. Okay, that would go up to 0.76. Okay, so that's within 3.77 there. We got this. This most recent work is, yeah, so it puts it within about a little less than 2 standard deviations away from the most recent or the CMS work. So basically, we're going to plot this out, which if I do actually turn this into a paper, I should do this. So this is the closest one here. Basically, this dot, just a hair to the right of it. This would be so basically we'd be going down here. So it seems to be within range of most of the things, with the exception of this outlier and this here. But then again, it would be within about 3.5 sigma of, oh, let's actually calculate that right now. We can do that. What's the standard model? Standard model is 3.53. I'm sorry, I'm reading off. I'm neglecting the 80 there because I don't feel like saying it every time. Uncertainty of 6. Okay, so let's do that. Okay. Put this in. Let's take our number here. Okay. Let's see. GEV. And then we'll subtract. Oh, we should probably put the decimal place in there, because otherwise that's going to be a good number of orders of magnitude off. Let's see how far. Okay, so it's 20 mega electron volts off. And divide by 6 MeV. By 6 mega electron volts. It's MeV. Why is it? Is it 4 sig? Is it? Oh god. Oh, it's... Why are... Okay, I'm just gonna write these in MeV so it doesn't just start rounding. Now, hey, MeV, MeV. Oh wow. No, it was right. It's literally 4 sigma out. I mean, I don't know. Maybe this just invalidates everything. It's outside by uh 4 standard deviations of the standard model. A little less than 2 from the measurement there. Then again, is that based upon other previous things? I don't know. Hey, maybe I just disproved everything, or maybe there's no basis at all because you look at reality. Now, again, I am very biased on this, but then again, if I just look at the chart here, it's like, okay, it seems to be like one experiment that's kind of seems to hit head on, and around times you're gonna see scattering and stuff. But I'm like, okay. Now, as long as it's not like these things are like, dude, I'm gonna keep my mouth shut because I often wonder. It's like some of these error bars. Can you just, I don't know, say there's at a what in doubt increase your error bars? I don't know. I just look at this. I'm like, well, this hits it. If I did say it was a little bit here, that 3.77, which is right about there, I'm like, it seems to fit most of the data within about 1 sigma, and it's also a little bit off there. And to be fair, I mean, if the Higgs boson, which I think they were using the Higgs mass of, I think like 125.118. Again, our Z boson mass from this calculation was Z was over here. It's on the top end of the 1 sigma. Okay. I mean, would we expect that to be a little bit magnified through? And again, I'm just data fitting with the simplest thing possible, or at least the simplest thing that might be able to tell a story why. It's, well, if you're looking at the vacuum expect or the Higgs self-coupling, again, with these baked-in assumptions, there are baked-in assumptions saying that I claim the Higgs boson mass is h bar, the elementary unit of action, divided by the joule second, the reference of action. We take the square root of that, multiply it by the Planck mass, and that is the mass of the Higgs boson. This happens to be basically right about what CMS recently measured it at, but that's a different discussion there. But, okay, we take that, and we go through the Fermi interaction, we calculate this out, we take this for the vacuum expectation value of the Higgs boson, we take the numbers from CODATA, we plug them in here, we get the Higgs vacuum expectation value with a couple of more significant digits. We go to the mathematical formulation of the standard model. We look at the Higgs self-coupling strength. This lambda thing is mass of the Higgs squared divided by 2 of that vacuum expectation thingy we just calculated squared. We throw that into the stuff. We compute the things. It gives us this number here that's 0.129, which apparently seems to be what the Higgs self-coupling strength is. Okay. Might we be able to see something a little deeper? Let's plug that number into Wolfram Alpha. Is there a closed form? The closed form that matches the best is this crazy thing here, 3 over that G sub GE. What the heck is that? It's Gelfond's constant. What's Gelfond's constant? It's e raised to the pi. That was unexpected. It also happens to be the sum total of all even dimension unit sphere volumes utilizing the series expansion here gives us e to the pi. Sum of all even dimension unit hyperspheres. I mean, that's kind of cool. We got a 3 there. Why? I don't know. Do we live in 3 dimensions? Who knows? But at that point, now we're dividing the sum of all even dimensional hyperspheres into something that's odd. It's not just going to straight up give us inverse as a natural number. Okay, that's kind of cool. I think there was one more thing we wanted to show here. Okay, it wasn't there. Let's go back. All right, so we've got those things there, and then we're continuing with our rampant speculation here. We take the recent measurements of the top quark, the combined data of ATLAS and CMS. Take that 172.52 gigaelectron volts with our error of 0.33. We compare it to our conjectured value of the Higgs mass. We get that 1.376. What might that be for a potential closed form? E to the root pi. Well, e to the root pi. That's... Wait a second. That's... Seems very similar to e raised to the pi, except we're just taking the reciprocal of pi. E raised to the 1 over pi is the pi root of e. We couldn't be so lucky. There's no frickin' way that this could actually be what's going on. I mean, again, this is a happy coincidence. As far as I'm considered right now, it's a happy coinkydink. Unless somebody a lot smarter than me can be like, oh, there's some group representation that we can explain these things and everything. And again, you're also going to have to measure the data. Again. So, let's go back. Okay. So coincidentally, we've got that ratio there. And then if we took that seriously, we take our, again, conjectured mass value for the Higgs boson, multiply it by the pi root of e, or e raised to 1 over pi. Get 172.37 GeV. That's well within the lower level of 1 sigma from the recent combined measurements from ATLAS and CMS for the top quark. Okay, that's kind of cool. We go to the mass of the Z boson. We got this number here. Let's do a space search. We look for the relationship between the Higgs mass and the Z boson mass, and 1.375, 1.376. It looks to be about the same magnitude and distance from the top quark to the Z boson. Why? I don't have the answer. I'm literally like trolling the internet, so to speak, trying to find what it might be, because, well, when you plug that number again, we find a similar value, except that was 6. This is 5. Okay, this is much closer for this one. It's kind of interesting. What happens if we do that? So instead of multiplying our conjectured Higgs boson mass by e raised to the 1 over pi, all we're doing is we're dividing it by e raised to 1 over pi. Okay? And then we get within 1 sigma towards the top end of the standard deviation for recent measurements submitted of May this year and last revised 3 days ago. Okay, so it seems to be at the top end of that. All right. And then we got the W boson mass. W boson mass, and again, here's where we fall out of 1 standard deviation. This will go up to 80.37. We got 80.377. So it's about 2 standard deviations away, and it's, according to the standard model, 4 standard deviations out. It's not new physics. It's within 5 sigma, so that seems to be the threshold. And again, it is outside of 1 sigma, so you got some splaining to do. The best splaining I got is this picture right here. Try a different combined. This is the standard model prediction. As you can see, most all of these hit the standard model with the exception of this one here by the CDF. But again, it's for a precision thing. It's there, but if we were to take the claim of this seriously, and again, this was calculated by basically doing the calculation for the Z boson mass, so just our conjectured Higgs mass that we get from over here, and well technically over here. I dropped the 1 just because I think starting it, and also just to bolster my argument, because again, there's a mass range there, and that's where it starts getting, yeah, that's where our error really starts kicking in. Okay, and then that had calculated that a ratio or way to complete the weak mixing angle, which is this guy over here, is if we utilize hyperbolic sine to the -1 of 1. AKA, it's, let's see. Oh, God, I just forgot that. Hold on, it's going to say right here. It's like log of 1 plus √2 or something like that. Log of 1 plus √2. Okay. That's kind of cool thing. All right. And again, this is a couple of standard deviations out, depending on how you want to take it there. But if the top quark was a little bit less heavy, the Z boson was a little bit more heavy, when you expect the W boson to maybe be as heavy? I don't know. Maybe something in that formulation I read over there will completely say, nope, this is wrong. Nope, nope, there needs to be a particular gauge between the W and the Z boson. I think I was reading about there. It's like, okay, we need to look at those ratios, and sometimes what they call like perturbation theory, where you tweak something a little bit, and you just kind of see what works. It's like, all right, you tweak it a little bit, and you try to hone in on what you have the most confidence in. Kind of like, basically what's supposed to be happening is in 2030, yes, 5 years ahead, apparently CODATA and everything, they're going to redefine the SI system again. Maybe not CODATA, but the International Society of Weights and Measures and stuff like that. Basically, long story short, is SI is going to be defined by the second. Why the heck might that be the case? Well, they already redefined it once to help link them to constants in nature. Well, those constants in nature, things like the speed of light, well, we've got 9 significant digits. Okay. H bar, we got to like 10 significant digits. We've now lopped it off. We defined it at 10. We used to have like 12, and there was some really large errors, so we just lopped it off, and like, we have high confidence it is S to 10 significant digits within our unit system. To be fair, the clocks are probably some of the best things that we have. If we're getting up into the range of attosecond clocks potentially, or even maybe some of the new thorium clocks, which personally I think would be awesome, because in my opinion, I just like saying we require more thorium. Basically, if the second is the most precise thing we have, probably not a bad idea to base things off of that. So, who knows? Maybe there's a tragic flaw that we're missing somewhere here. But so that's kind of cool. I just kind of wanted to go over this. That I don't know might where, oh God, Gelfond's constant, maybe some simple thing, or maybe not simple, but some relationship in reality that maybe pops up somewhere, maybe could pop up somewhere else. And I've seen this pop up before. I didn't pay it really much attention until it's like, oh, let's calculate the the Higgs self-coupling constant. It's like, all right, the thing that matches the best, that's the simplest, is 3 divided by Gelfond's constant. Like, oh, what was this constant again? Oh, e raised to the pi. So the best fit for the Higgs self-coupling constant is 3 divided by e raised to the pi. I mean, that would be fantastic if it was true. And again, I'm looking for things that can make things simpler. If you got a 3, you got an e, you got a pi. Can we simplify or perhaps computationally reduce? I don't know. Maybe some of all this stuff here. I don't know. Maybe we need all this. Maybe we just need a lot more stuff. Maybe this is the most computationally reduced form that we have. We can't do any better. That may possibly be the case, but I'm thinking, again, that number right over there, this crazy thing just comes from this. Just taking the Higgs self-coupling strength. Lambda is defined as the mass of the Higgs squared divided by 2 of these vacuum expectation values squared. We do that thingy here, 2 conjectured Higgs masses divided by these, the vacuum expectation values squared, and then 2 of them, and then we get this number here. That seems to match, be the best fit. It happens to also be the sum of all even dimensional unit spheres. It's and we just happen to be divided into something that happens to be a 3. Okay, that's an interesting coinky dink. And then you look at the ratios between the Higgs mass and the top quark mass. Oh, look, this is e raised to 1 over pi rather than e. I'm entertaining the idea. Maybe there is some there because it seems to generate the top quark mass within the current best constraints there. As far as the Z boson mass, it seems to be able to calculate it to the upper end of 1 sigma. And then with the W boson mass, it is within 2 sigma and about 4 sigma out from the standard model prediction. So just, again, take that for what it's worth. And again, my best argument over there is, well, most of the things seem to be falling kind of over here, which is a little bit outside. And again, this was, I think, like 40 or 50 sigma out. I don't know if we're within, I don't know, about 4 sigma-ish. It seems to match all these things. And again, this is incredibly hard. You're trying to smashing protons and stuff together at like near the speed of light to an observer like us, and then trying to reassemble the absolute catastrophe that happens. Then again, I heard the CERN beam luminosity hit like 500 femtobars to the -1 or something like that. It's, long story short, it's like a magnitude of like 10 to the 45 or 5 times 10 to the 45. It's a ginormous number. Long story short is they only hit like 100 inverse femtobars like 3 days ago. I think the Higgs was discovered at about 5 inverse femtobars or something. So at least if the luminosity goes up, does that allow us to see things better so we can better tune our ways to parameterize these things? Because I think it was Professor Beecham at one point had said that, well, until CERN's recent upgrades, they were literally only recording like 1 out of like, I don't know, 40 million or 40,000 events. I realize that's a ginormous difference, but I'm like, they were literally, they throw away the vast majority of the data because it's too much data to store. They need to see and look for particular decay style events, model them out as best we can, and then help figure out these calculations. The sheer fact we can even conceptualize to try to do something that phenomenally crazy, I think, is a testament to humanity. That's where I'll stop my soliloquy for tonight. Oh, very cool, very cool. Bahamut University. Basically. Oh, cool. No, thank you, Rick. No, that means a lot. Again, I'm just looking for the most simplistic things that we have. It's kind of like, I don't know, there's some things as human beings that like really resonate with us because it's like, well, everyone enjoys a good story. Everybody loves music. There are certain things that I think, as Stephen Wolfram might say, observers like us resonate with, and we've explored to certain degrees. I'm going to claim that there are some places where it might be worth further exploration. And with that, I'll stop wasting all of your time. So hey, thank you all for watching. Peace out, everybody. Take care of yourselves. It's a wacky, wild world out there, and just hoping we can level up humanity at some point or another. Take care, y'all.